Now unbalanced three-phase three-wire Y connected load. So now we are considering the Y connected, but it is three-wire. So obviously that neutral point is not connected right now. So this could be either YY system, just like our previous one. So in that scenario, obviously the neutral was not connected. That's why this could be a three-wire connection. And also this could be delta Y system, because we know that in delta connection we have no neutral connection and we have just three wire. So this could be either YY system with no neutral connected, or this could be delta Y system. So this could be a typical load. So these are three branch impedances Z1, Z2, Z3, and they are not equal since we are considering the unbalanced phenomena. And these are the phase voltages VAN, VBN, VCN, and these are the phase currents IAN, BN, CN. And if you notice closely the notation, that is here it is plus and it is minus. So here also this is plus and this is minus for VAN, and for VAN this is plus at the terminal of the source connection, and the minus of all three are connected to here neutral point. So you know this general form. And then this EAB, so this is basically the line voltage from A to B. That's why at point A we have given the plus symbol, and towards point B we have given the minus symbol. And since this is ECA, that's why this is plus towards our phase C, and this is minus towards our phase A. And similarly the EBC as well. Now apply the KVL. So this is not new. Whenever we have derived the expression of relation between the phase voltages and line voltages, we have already used this sort of formula. So here a loop is formed. So if you consider this a red loop, and then if we apply a Kirchhoff's voltage law, then this should be minus EAB, then plus VAN minus VBN. So from where it was just like this, minus EAB plus VN minus VBN. So from where you can write EAB equal to VAN minus VBN. So this is not new. Don't feel difficult, because we have used this expression previously whenever we have derived our expression. So previously I have showed you just like this. Let's say AB. So EAB, this should be this, let's say VAB. So this should be VAN, then since this is minus in this direction, so this should be minus VBN. So I can write VAB equal to VAN minus VBN, and this VAB basically EAB. If you notice here, so this VAB, if I call it V at the load side, so this is basically connected to generator side, since we are not considering any transmission line impedances. So that's why this EAB and VAB are equal, and I can say VAB is basically VAN plus VNB, and we can say again minus VBN. So this is actually written here. And if you want to justify it using KVL, you can also do this, and the KVL justification is given here. So by this process you can get the EAB equal to VAN minus VBN. And similarly, if you apply another KVL at the blue loop, so here another loop is here, this one from ECA and then Z1 to Z3, so another loop is formed, and you apply another KVL, then you will get the result just like this. And this is also shown in previous calculation, and also you can verify just like another way. So let's say this is a C branch here. Let me clear this all. ECA. So if you want to calculate ECA, so from the C to A, so I can say this is basically VCN minus VAN. Since this voltage ECA is from here to here, so this voltage I can say this voltage plus this voltage. So this is basically a KVL, I can say also. So from where we can write this expression, and also we can write the expression for EBC. Now if you want to solve the phase current, that means from this circuit, if you want to determine the phase current, that is IN, BN, CN, so we know that the voltage equal to current multiplied by impedance, right? And previously I just shown in another method that this current basically that phase voltage over impedance. So from that expression I can also say voltage equal to basically that phase current multiplied by the phase impedance. So similarly VBN equal to IBN Z2, VCN equal to ICN Z3, and then if you put this VAN, VBN and VCN values in previous expression, that means this one EAB, ECA and the last one was EBC, right? So if you put these values, then the expression will be just like this. And here again if you notice, this is basically three equations, and if we consider this value are given, that is EAB, BC, CA in question, and if you asked to determine this I, A, N, B and C, N, so this is basically three unknown and we have three equations, so we can solve these equations and get the required values of I, N, B and C, N. And also if we want to convert this three equation to two equation, then that's also possible. So if we want to apply KCL at node N, so previously that IN, BN, CN equal to IA capital N, right? From previous math we know. So for this three wire connection, obviously this there is no IN, since there is no connection to neutral point. So you can say IN plus BN plus CN equal to 0. And again if you want to justify it using applying a KCL, so you can also do that, that will be no problem. So at that point N, I can say this ICN is entering, IAN is also entering and IBN is entering. So I can say the summation of these three currents should be 0, because we know the algebraic sum of current entering and leaving is 0 for KCL. So from where we can write these are equal to 0. And then if you want to determine any value, so if you write IBN equal to, then it will be minus IN plus ICN. And if you feel you want to calculate IAN, so you could write it IAN equal to minus IBN plus CN. You can also write this, and then you can put this value to our previous expression. So just like they are given here. So now if you notice EAB, so this is previously INZ on minus, so this IBN is now shifted by minus IN plus ICN. So this value is given, and then if you further simplify it, so it will be simplified later on here. So this equation is simplified to here. So if you notice EAB equal to INZ on, then we have another IN here. So if you take that IN as the common term, so it will give you Z on, then minus minus, it will give you a plus, then Z2. And similarly we have minus ICN Z2. And again for second equation, so we have another equation here. So if you put that values here, so EBS equal to IBN Z2 minus ICN Z3. So if you put that IBN value, so it will give you just like this one, and where you can take the ICN as the common term. So this expression is written here. So it will give you minus IN Z2, or I can say IN into minus Z2, and then this ICN, so you have another ICN here, so you can write it minus Z2 plus Z3. So these are simple representation, so you can do this I think. And now we have just two equation and two unknowns. So what are the two unknowns? One is IAN and ICN. If we consider this line voltages are given and also the impedances are given, then obviously these two currents are unknown quantity. And we know from our mathematics background that if we want to solve some equation, then the number of unknown should be equal to number of equations. Since the number of unknown is 2, so by using only two equation we can solve this. So by using these two equation we can determine the values. So we will be observing this in a math, so don't worry. So this is the example problem. So this is a three-phase, three-wire connection, and this is a Y-connected load. So the impedances are given, and since it is a unbalanced problem, so the impedances are unequal to each other, and the line voltages, that is EAB, EBC, and ECA, these are given, and also the frequency are given. So first of all, let's calculate the impedances. So here at phase A, the capacitance of 16 microfarad was given, so there was no ohmic value was given, and we know that we basically need the impedance, and we know the impedance formula, Z1 equal to minus J into XC, and then we know X equal to 1 over omega C, then we know omega is basically 2 pi F. So if we put the values of F equal to 60 Hertz, it was given in question, and capacitance value was given at 16 microfarad, then we will get the Z1 value in terms of ohm, and similarly the Z2 and Z3 are already given, so don't worry. And in question it was asked, find out the phase currents and phase voltages for each phase of the load. All I have shown here, these equations, that is first of all EAB equal to VN minus VB, and then ECA equal to VCN minus VN, this calculation or these equations basically shown here. So I think you can understand, because I just showed them, EAB equal to VAB, VN minus VBN, and similarly for EBC, ECA, then this VN equal to this are given. So this derivation I already shown you just now. And finally, you know that we got two equations just like this, and where this IAN and ICN are unknown. So these two equations are already shown previously, and for these circuits we know the value of EAB, BC, and also the impedances. So now if we put those values, so that EAB, BC was given here, and also the impedances, if we put those values, so now the expression is just like this, and we know that we can solve this two simultaneous equation using Kramer's rule, right? So this Kramer's rule, we use determinants, and for first IAN, that means this value I can calculate it. We know that in denominator we have a determinant of consisting of this these components associated with the variables that we want to determine. And for IAN, at the numerator we should have these constant terms the place of this IAN. So 200 angle 0 degree, and for the second one 200 minus 120 degree, these are given. So I think you already know this Kramer's rule solution process. Again, if you feel this complicated, or if you find it difficult, don't worry to research. So using this Kramer's rule, we can determine the variables, unknown quantities, that is IAN, and similarly we can determine the ICN. And you know that previously we have basically given the values of IBN equal to minus IAN plus ICN. So if we determine the values of IAN, ICN previously, then we can put those values in that equation, and we will get the values of IBN just like this. So all the phase currents are being calculated. Now if we want to calculate the phase voltages, then we know the phase voltage equation, that is VAN equal to basically IN multiplied by ZN, and for VBN it is basically IBN Z2, and for VCN it is ICN Z3, and these impedances all are calculated previously. So if you put those values and calculate this using calculator or manually, so you will get this result. So these are asked the phase voltages and phase current, so I just shown you.